In this learning module, we're going to cover the concept of position vectors. Position vectors have a lot of practical usefulness for us because kind of measurements in a Cartesian framework are so easy to make. So oftentimes we'll have scenarios where we have a force acting upon a body and we know kind of the general direction of that force because it's determined by the load-bearing object. In this case, the particular figure that I have to the right, we have this cable, which is serving to pull on the boat in order to keep it stable through anchoring to the buoy here on shore. So we know that the force is directed from the point of connection on the boat to the point of connection here at the shore. So if we were to know the magnitude of that force, but we wanted to describe it in rectangular kind of coordinates in order to use all the techniques that we've spoke of up to this point in the chapter, we would need to be able to have some knowledge about its direction in order to do the decomposition. And the way that we can do that, one of the easiest ways, is by using position vectors, as we'll see in this learning module. And what makes it so easy is it's very simplistic to take relative measurements of the position of one point of connection to the other. I can measure this height easily. I can measure the separation from shore. I can measure how long down along the shore it is. So we'll see how that actually becomes useful in the next few slides. So a position vector just basically measures the displacement from one point to another. So if you just focus on this figure over here to the right, R is a position vector from A to B, and that from A to B really matters. The direction obviously is unique here. If you change your starting and end points, you'll get the same line of action of the vector, and it will be the same length, but it will be rotated by 180 degrees. So in order to keep the notation clean, we use subscripts. RAB is read as the position vector from A to B. And the way that we define it is we take the individual coordinates of point B and point A, we subtract them kind of on an individual basis. What I mean by that is subtract the x coordinate of B from the x coordinate of A, use that difference to scale the unit vector I hat, do the same thing for the y coordinates along with the z coordinates. And what that gives us is a position vector from A to B. So tip would be at B, tail would be at A. Key point, don't mess up the ordinate of your coordinates when you do that subtraction. So how can you actually apply this to describe or model forces where you know their magnitude and you know their line of action, but the line of action, you only really can describe it by having 2 points along that line? Well, we can use position vectors. So in this example, we have this cable, which is exerting a force on this hook, which is anchored here into the wall. If we were to have coordinate descriptions of A and B, since these are kind of along the axis of the cable, and we know that this force is directed along that line of action, we could use our position vector technique. Well, that would give us a vector from A to B, and we know that that would have the same direction as the force. But how do we kind of get rid of the effect of magnitude? And the way that we do that is we take that position vector and we scale by its magnitude. So what's going on over here, the reason that we're doing this is in order to kind of normalize the position vector and make the resulting vector, which is the force, have the original magnitude that we know. So again, in the case where we know the magnitude, if we know 2 points along the line of action, find a position vector, normalize the magnitude of the position vector out, and then that will be a unit vector, and scale it by the force magnitude. So in terms of an example problem, assume that here in our drawing we see that this cable is kind of exerting an 840 Newton force on this pole, pulling it along the line of action that's described by a position vector from A to B. How would we write that force B in rectangular coordinates? Well, using the approach that we described beforehand, and kind of pause the video and think about it for a minute to make sure that you know how to do this. What we want to do is write a position vector from A to B, RAB. Once we have that, we'll find the magnitude of that position and normalize it out in order to get a unit vector that points along that direction. And then we'll scale that unit vector by the magnitude of FB. So that's kind of the steps that we're going to take. So in order to start that, how will we start it? Well, the first thing is we have to describe the relative coordinates of A and B. Now, fortunately for us here, they've kind of drawn in a coordinate system. So if you notice point A, that's located along the z-axis, so it has no x or y displacement. Its coordinate would simply be 0, 0, 6. Point B, how do you get from the origin to B? Well, along the x-axis, you'll notice that we're dimensioned here. We have 3 meters. You come out 3 units in the positive direction. From there, In the y direction, you'll go in the negative sense, since positive y is this way, by 2 meters. That will take you to point B, right? Because point B is kind of in the xy plane. There's no z elevation there. So next, we just need to apply our definition of the position vector from A to B by taking the coordinates of B, subtracting them from the coordinates of A, and then taking each result and scaling it by the appropriate unit vector. That gives us 3 minus 2 minus 6. And we can kind of check that that is right by asking ourselves, okay, in order to go from A to B, do I move in the positive x direction? Yeah. Do I move in the negative y direction? Yeah. Do I move in the negative z direction or down? Yes. So kind of do a sanity check at each point of the problem. Going back to a couple learning modules ago, we can determine the magnitude of that vector by simply taking the square root of the sum of the squares of each of its components. If you do that, you get a magnitude of 7. Find a unit vector along that position vector from A to B by scaling the position vector by its magnitude. Remember that when you scale a vector, you just scale each component individually. And finally, what we want to do is take that magnitude of the force that we were given and multiply by the unit vector along the line of action that we just computed. That will be 840. If you notice, I'm going back to my shorthand here to make the math fit all on one line. So take the 840 Newton magnitude, scale it by the unit vector along AB, and that kind of looks like a distribution, even though this is technically a vector. But again, that's consistent with the rules of vector scaling. And what we get is a force that has an x component of 360 newtons, a y component of minus 240 newtons, and a z component of minus 720 newtons. Good to go back and do a sanity check and make sure that the relative signs of your force vector are the same as that of your position vector: positive, negative, negative, positive, negative, negative. So that checks out. So pretty easy concept, but pretty powerful nonetheless.